Alright, number 1 for 5.5a, they ask you to use the rational root theorem to list all the possible rational roots. Okay, so for this one over here, what you want to do is you want to look at the values for your constant, which is going to be -9, and that's going to be your p, and the value of q, which is going to be your lead coefficient. And what the p and q do is you want to find out all of the factors of p, all of the possible factors of 9. So we're going to have 1, 3, and 9. Then we want to write down all the factors of q, which is 1. So that's going to be 1. So our list is going to be 1 over 1, 3 over 1, and 9 over 1, which just simplifies down into positive -1, positive -3, positive -9. Then they want you to find any actual rational roots. So what we want to do is graph this function. So x cubed plus 2x minus 9. And then look at what this value will be here to see if it matches up with any of these. So second trace 0. Left bound is right under it. Right bound is above it, and then guess. So our 0 is supposed to be at 1.76, so on and so forth. That value doesn't correspond to any of these values. So that means that if you would have tried all of these values using synthetic division in here, none of these would be a factor. And if none of those are a factor, then none of these can be any rational roots. So we would say no rational roots. Number 2 is the same thing. So our p is going to be factors of 1, so that's just 1. Our q is going to be factors of 8, so 1, 2, 4, and 8. So that's going to give me possibilities of 1, positive -1/2, positive -1/4, and positive -1/8, because we want to look at it as 1 divided by 1, 1 divided by 2, 1 divided by 4, 1 divided by 8, with all the positives and negatives. So those are all of my possible rational roots. Now let's graph this and see which of these make sense, or are roots of it. So we're going to have 8x to the third plus 2x squared minus 5x plus 1. Alright, so if we zoom in a little bit on here, we can see a little bit closer what our roots might be. Alright, so it looks like it goes through -1 over here. And we can confirm that by looking at the table and going up to see what the output of -1 is. It's 0. So we know that is a fact. So we know that -1 works. So what we're going to have to do now is we're going to use synthetic division to show that -1 works and deconstruct this. So -1 going into the coefficients, so 8, 2, -5, and 1. So bring the 8 down, multiply, add down, multiply, add down, multiply, add down. So we see that the remainder is 0. That proves that x plus 1 is a factor. So we could rewrite this as x plus 1 times 8x squared minus 6x plus 1, which is the quotient here. Now what we want to do is we want to find another rational root, if we can. So let's find out what this root is over here. So if I do second trace 2, I approach it just before, enter, right bound is just after, and then guess 0.25. That corresponds to 1/4 here. So let's do 1/4 using synthetic. And we're going to use that with the 8, negative 6, 1. So bring the 8 down. 1/4 times 8 is 2. Add down. 1/4 times negative 4 is negative 1. Add down. And we have 0. So this shows that 1/4 works. And that means that we can continue the factorization here. Because this is true, we not only have x plus 1, we're going to have 4x minus 1. So x plus 1, 4x minus 1 times 8x minus 4. We can continue to factor this because 8x minus 4, you can take out a 4 from here. So if I do that and put the 4 way on the outside, if I take 8x divided by 4, I'm going to get 2x and then minus 1, because negative 4 divided by 4 is negative 1. We don't have to check that last one. We know it's going to be 0.5 because this is a 0 of 0.5. So the ones that work were negative 1, 1/4, and 1/2. And those are your 3 zeros. All right, a polynomial function with rational coefficients has the given roots. Find 2 additional roots. Well, if you're looking at this, the negative 2i is imaginary. That means we have to have its conjugate, positive 2i. The root 10 is irrational. That means we have to also have the conjugate of this, negative root 10. So there are your 2 additional roots, positive 2i and negative root 10. All right, write a polynomial function with rational coefficients that has the given roots. If you're scanning the roots here, we have 4, 16, 1 plus 19i, and because this is imaginary, you have to have its conjugate, 1 minus 19i. So now we have to write a polynomial function with rational coefficients that has these roots. I'm going to lump these two together. So the 4 and the 16 together is going to give me a quadratic. The sum of these is 20. So the opposite of the sum, remember, is the coefficient of the x term. So the opposite of 20 is negative 20. The product of these is going to be my constant. So 16 times 4 is 64. These are going to give me another quadratic because there are 2 roots here. If I add these together, the i's will cancel, and I'm just going to be left with 1 plus 1 is 2. The opposite of 2 is negative 2, so that's going to be your middle term. The product of these might be a little bit tougher to figure out, Because they're conjugates, the O and I in FOIL will cancel, so I don't have to do that. So the F is 1 times 1 is 1. The L is a positive times negative, negative. 19 times 19, which if you do that out on your calculator, comes out to be 361. And then I times I is I squared. I squared is negative 1, so that's going to change the sign here. So it's going to be 1 plus 361, which is 362. Now what you're going to do here is you're going to just distribute all of that stuff out. So x squared times x squared, x to the fourth. X squared times negative 2x is negative 2x cubed. X squared times 362 is 362x squared. Now the middle term, negative 20x times x squared is negative 20x cubed. Negative 20 times negative 2x is positive 40x. Negative 20x times 362 is going to be negative 7,240x. Got some crazy numbers here. Then we do 64 times x squared. Get 64x squared. 64 times negative 2x. 64 times 2 is 128, so negative 128x. And then 64 times 362 is 23,168. Crazy numbers. Alright, so let's add what we can and then we'll be finished. We only have 1x to the fourth. For the cubes, we have negative 2x cubed and negative 20x cubed. That's going to be negative 22x cubed. For the x squareds, we have 362x squared plus 64x squared is going to be 426x squared. Then we have 40x minus 7,240x minus 128x. That's going to be negative 7,328x. And then plus 23,168. That's one crazy answer. Number 5. What does Descartes' rule of signs say about the positive real roots and negative real roots of this? Alright, so what I typically do is I write down what p of x is, and then I write down what p of the opposite of x is. And when you do that, basically you change the sign for any odd numbered term. Because if you put in a negative x in here, negative x cubed is negative x cubed times a 9 is going to give you negative 9x cubed. So you see, with an odd power, it's going to change the sign of the term. But with an even power, it's not going to do anything to it, because negative x squared is positive x squared times a negative 4 is negative 4x squared. And this isn't going to change sign. So what you do with Descartes' rule of signs is you count the number of times that the signs change. So we have a positive to a negative, that's one sign change. And then negative to a positive, that's two sign changes. So we have two sign changes. That tells me that you're going to have 2 or 0 positive real roots. The p of x number of sign changes tells you the number of possible positive real roots. It's either going to be 2 or 0. And why is it 0? Why isn't it 2? Because there's 2 sign changes. Well, Descartes' rule of signs says that it's either equal to the number of sign changes or less than that by an even number. So if you take something less than 2 by an even number, it's either going to be 2 or what's the smallest even number? 2. So if I decrease 2 by that even number 2, you get 0. Another example might be if you have 6 sign changes, then you could have 6, 4, 2, or 0 positive real roots. This one over here, the p of the opposite of x, tells you the negative. Talks about the negative real roots. So how many sign changes do we have here? That's not a sign change. That is a sign change. So we have 1 negative real root. Why don't I decrease this by an even number? Well, if I did that, that would be 1 minus 2 would be -1. You can't have -1 real roots. That wouldn't make any sense. So this is your answer. Find all the rational roots for this one. So let's write down all the factors of 14 here. We're going to have 1, 2, 7, and 14 divided by all of the roots of 7. So 1, not roots, but all the factors of 7, and 7. This is going to give me a list of 1 here, 2, 7, 14, that's all of these over 1, and then we have to put all of these over 7. 1/7, 2/7. I'm not going to bother with the 7/7 because that's the same as this. And I'm not going to bother with the 14/7 because that's the same as 2. So here's my list of all possible rational roots. So what I'm going to do now is I'm going to check the graph of this and see which one of these roots I'm going to use for synthetic division, if any, because there's a chance that these could all be irrational. Let me just zoom out here. Alright, so it looks like we only have one root here, there. So let's find out what that value is. Second trace 2. There it goes. So there's just under, that's my left, just above, that's my right, and I'm going to guess negative 1.395. Do any of these look like negative 1.39? It's not that, not that, not that, not that. This is not larger than 1 or less than negative. I should say this is not less than -1. This is not less than -1 either. So none of these correspond to that 0. So that means that there's no rational roots. Alright, divide using long division. So we have 4x cubed plus 21x squared minus x minus 24 divided by x plus 5. So x times what is 4x cubed? That would be 4x squared. That times that is 4x cubed. 4x squared times 5 is 20x squared. Change the signs, add down. That means we're going to have a positive 1x squared. x goes into x squared x times. When you multiply, you change the signs. Add down, that gives us negative 6x minus 24. X goes into that, negative 6 times negative 6 times x, negative 6x, negative 6 times 5 is negative 30. Change the signs, add down, and we have a remainder of 6. So this is your answer right here. Alright, divide using synthetic. Let's write our list of coefficients here. So the x to the fourth is 1. We don't have an x cubed, so we have to put a 0 there. X squared is negative 6. The x we don't have, so we have to put a 0. And then negative 27. And we're going to do negative 2 into that. Drop the 1, multiply, add down, multiply, add down, multiply, add down, multiply, add down. So there's our remainder, our constant, our x squared, and x cubed. So our answer is x cubed minus 2x squared minus 2x plus 4 with a remainder of negative 35. Alright, so determine the end behavior and the number of turning points. So it's an odd power, so that means we're going to have split ends. So we're going to have the limit as x approaches infinity, and we're also going to have the limit as x approaches negative infinity of the function. So for this one it's positive, so that means it's going uphill. So as you go toward the left, it's going downhill. So this is going to be negative infinity, and this is going to be positive infinity. Just to throw a cubic might look like something like this. As you go to negative infinity for the x's, you go down to negative infinity for the output. If you go right to positive infinity, you go up to positive infinity. So there's your end behavior. The number of turning points, let's look at the graph of it. Three x to the third plus 4x squared plus 2x minus 1. So let's take a look at this closer here, just to see if we do have turning points here. Well, it doesn't look like to me, because it doesn't look like you're ever going downhill. It doesn't look like you're changing directions. Like you're going up, up, up. It kind of flattens out, but you're still going up. And then up, 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 up. So you're not actually turning anywhere. So it kind of flattens out. So this one is not going to have any turning points. So no turning points for this one. And number 10, a quartic equation with integer coefficients has 2 real roots and 1 imaginary root. Why must the fourth root be imaginary? Well, if you have 1 imaginary root, let's just say we have the 2 real roots, let's say it's negative 4 and 1. Let's say the imaginary real root was 1 plus 3i. The fourth one has to be imaginary because this has to have its conjugate pair. So the reason why is because of the conjugate root theorem. The conjugate root theorem states that if you have real integers for your polynomial and you have any imaginary or irrational roots, they have to come in pairs. So you have to have its conjugate pair in addition to that, and it has to be imaginary.